glitch there in the video. Again, I'm having some trouble with YouTube Live, but I am streaming live. However, if you are watching this as an archived video on YouTube, not watching this live, I would encourage you to check this video's description, as there will be links to time codes where certain tutorials happen, as well as actually links to the edited, finished versions of these tutorials, which you might just want to go ahead and watch. Please in the chat, let me know if this is working. In fact, I do see on my preview screen that it seems to have, it says stream resumed, that I am live. I should be live on YouTube, and I should be live on Twitch, and I should have a screen behind me. Now, I had to unplug and restart and do a bunch of things, so a few things are now not set as they normally would be. I will set those as I continue, but let me first just say hello and introduce myself and begin and talk about a little bit what's going to happen in today's session. Can you please in the chat tell me that you see me, because I don't actually see myself in the preview. Shoot. I'm going to hit, oh, I do see myself in the preview now. Okay, great. Okay, so hello, my name is Dan Schiffman. This is my YouTube channel, informally known as Coding Rainbow. And what I do in this channel is make tutorials, answer questions about creative code, making art with code, or just sort of learning how to program in general. And the environments that I tend to use most often are behind me over here, something called processing, which is Java-based, and something called P5, which is JavaScript-based. And today what I intend to do is talk through how to simulate a chaotic system known as the Lorenz Attractor, and I'm going to use processing and I'm going to use 3D in order to do that. So that's kind of my main topic today. Before I get to that, I need to just set up. I kind of screwed up my whiteboard camera, so I have to fix that so I have that accessible. And then I also want to see if people have general questions in the chat. And also I have an online course that launched with a company called Cadenza. It just launched a couple days ago, and I said I would answer questions if people had questions about session 1, which is about random walker and vectors and P5.js. And there's actually a really interesting question that came up about on the forums there about the keyword this in JavaScript and sort of public versus private variables. Maybe I'll talk about that a little bit today, because I'm sure you all woke up this morning thinking, oh, I wish somebody would just turn on a YouTube stream and talk about the keyword this in JavaScript to me. Okay, so I'm looking at the chat. I don't see, okay, I see live again. Okay, I see encouraging words in the chat like I'm actually working. So I need to come over to the computer over here, which is this is where I have a, and I need to just fix this whiteboard shot. So hopefully this is going to be a really quick thing. That worked. And then I need to do one more thing, which is source settings. I'm just going to fix one other thing, which is I need to select this button. That should have done it. Brilliant. Brilliant. Okay, so you see that there, whiteboard there, you see me here. There was one other thing which I needed to make sure I did before I started. I know what it is. I'm wearing the same shirt as in the video. Yes, this is my video recording shirt, if you didn't notice it. I just also want to check my video channel, my YouTube channel, because I tried to start the stream like 3 or 4 times, and sometimes it leaves these like stray extra videos on the channel. So I'm just looking right now on this laptop under my video manager to see if there are some, by accident, extra videos like May 5th. Yeah, so these look like I'm going to make these private so you don't watch them by accident. Okay, yes, I understand that I can't undo this. And once it started, it started. Okay, yes, yes, submit. Okay, so hopefully you're still seeing me live. Everything going well. So the first thing I'd like to ask you guys is, and I got to get back to the chat here, live on Twitch, yep, is, yeah, so the first question, how do you pronounce cadenza? I think, and that's why I've been saying it. So let me just come up here and say cadenza. This is my current cadenza course called The Nature of Code, which you can enroll in and watch videos for, and I will answer questions about in a moment if people have them in the chat. I am pretty sure that the way that you pronounce it is cadenza. Cadenza, like cadenza and the letter A. Cadenza, cadenza. Somebody tweet cadenza official on Twitter and ask them if I'm pronouncing it correctly. And I've got 26 people live here. I was going to send out an announcement to the course list that I am doing this, and I will definitely do. I mean, the course is going all the way through mid-July, so I'm going to do. And as some of the topics get a bit more sophisticated, I'm going to do some live sessions just about that week, which I think to answer questions and that sort of thing. But was a little hesitant to use Cadenza's email blasting system to announce this because I don't want to be spamming people, and I don't want to be a sort of like look like I'm just like promoting random stuff. But I will think about a thoughtful way to do that in the future. I'm vamping here to see if people ask any questions. Put the link to Nature of Code in the description. Yes, so in fact, it takes some time, but after this video gets archived, Mathieu, who is from Canada, has been helping me with editing videos and uploading them and writing descriptions. He's doing an amazing job. And so usually, within 24 hours, he's got the time codes noted down and written into the description. So that's been like a wonderful, super help because that's one of my, I think that I'm good at turning on record and talking, but I'm not so good at the after the fact, like keeping things organized. So that's hopefully going to be a help. Okay. So, all right, so I don't see a lot of questions in the chat right now. I might check the forum. Actually, it would be sort of fun to just check the forum right now, here live, and see if there's any questions there. But I don't know. Maybe I'll do that in a minute. But what I want to do is talk about the Lorenz system. So I'm going to at some point start what I hope will be about a 10 to 15 minute tutorial where I build this Lorenz system from scratch. But what I want to do first is talk through some of the kind of conceptual details behind what this system is. And so that I can kind of, maybe you guys will help me with this a bit in the chat if I'm getting things right or wrong. What is a differential equation? What does it mean in terms of like mathematics and calculus, and what does that mean in terms of actual like code and writing things in software? What does it mean for something to be a chaotic system? What does it mean for something to be a nonlinear system? Where did this Lorenz system come from? So I want to kind of like look at Wikipedia and some other resources and talk through that stuff, and then I will start the part where I actually just program the thing from scratch. Okay, now I see some questions in the chat about the Cadenza course. So I'm gonna answer those now, and then we'll get back to this Lorenz stuff. Okay. When creating vectors inside of functions, you don't have to initialize them, is the question asked by Kurt Strong. So let me actually see if I can pull up one of the examples. I'm going to open up this P5 editor. I actually probably have an old version of the editor. No, it didn't yell at me. And so now I want to say open and documents and where? Okay, let me do something really quick. So by the way, the Cadenza course, just to for those of you who might be a little confused what I'm talking about, I mentioned already that I have this course on Cadenza. This course is being taught about physics, systems, and natural systems using JavaScript and P5.js. I also have a book at natureofcode.com. The book is entirely available online as HTML. The book is written with processing/Java in mind. I'm actively working on a JavaScript version of the book, which will come out at some point this summer, hopefully before the Cadenza course ends, if I can get it together. And on GitHub, there is a repository, a GitHub repository. I'm going to zoom in on it now. This particular link, github.com/Schiffman/the nature of code examples. This is where all the example code is for the original book written in processing. If I were to just go over here and type -p5.js, now I am at the repository where all of the examples in p5.js are. And I actually want to go back for a second here and show you what I meant to show you down here is also many people have contributed ports of all of the examples to other languages. So you can see there's a bunch of versions of it in Open Frameworks, which is a C++ framework, a bunch of other JavaScript ports, a Ruby port. So if you are doing that, maybe you're making them all in Unity, let me know, submit a pull request, add it to this README. If you don't know how to submit a pull request, I made a whole video tutorial about that. I got to get back to the questions. But the reason why I'm showing you all of this is because I believe if I go to dash cadenza now, oh, nope, I have to find this. Here it is. So this is a little bit redundant, but because as I made the video tutorials for the course, little things about the code were like slightly different as I was like kind of doing it live. So I have an entirely separate repository, mostly redundant from dash examples dash p5.js, but if you want to follow this one along, and the reason why I was doing this now is I'm going to quickly just download this repository and open up the random walker example, which I believe is what Kurt in the chat is currently asking about. So, whoops, let me go here and I think I will open up this one. Is this using, oops, can I use it? Can I do that? Yes. Yeah, okay. So let's see if I can now read Kurt's questions again and answer them as they reference this particular example. And this is, by the way, just a really, really basic, simple demonstration of a random walk. An object on the screen that has a position, and that position changes randomly every frame. So let me go back to the chat and see what these questions are. When creating vectors inside of functions, e.g. walker, do you have to initialize them? So I'm not sure I entirely understand the question, but let's kind of look at this. So I would say that, so a couple things. One, this walker function is a special kind of function. Now, it's not special because of anything it's not special in the way that it's actually written. It looks just like any other function. Syntax-wise, it's exactly like any other function. Function, name of the function, arguments. However, I'm choosing to use it as a constructor function, meaning a special function that generates objects. And you can see that because I am executing the function not just as calling the function on its own, but with the new keyword. New, call the function. That means the function's job is to make an object and return that object. Now, the reason why it's capital W is just convention. So this entire program would work exactly the same way if I made that lowercase w, but it would completely break if I take out the new keyword. Now it doesn't work. So the new keyword is really, really the only thing in the code that's actually saying, I want you to execute this as a constructor function. The capital W is just a convention for me visually to see that I capitalize my constructor functions. So I would say that the vectors that I'm using in the constructor function, they do have to be initialized. In fact, they are here. So position is, but position is a vector that's part of the walker object, and so it's created and initialized and attached to this keyword. Maybe I'll talk about that for those of you that might be confused by that later. And velocity here is just a temporary local variable for this particular example. So they are initialized. Do you think about joining the vectors together when adding vectors in future code example thinking? So, so this is interesting. So what's happening here is there are two vectors. There's a position vector. There's a position vector, which maybe sets the position of an object. And then there is a velocity vector, which is explaining how that object should move over time, or just for that particular frame. So the next location of the object is here. So I'm adding those vectors together. Position plus velocity equals this vector. So in a way, adding is like joining vectors in that the operation is you're putting them end to end. But what I'm doing is saying position plus velocity and then resetting that to position. So now the next position is defined as here and the circle is drawn there. So hopefully that answers that question. In P5 editor, why are w.update and w.display highlighted differently? That's interesting. So I don't see them as color differently here. Oh, they are here. Interesting. Okay, so I have a feeling this is, I wouldn't say like a bug exactly, but I have a feeling that display is some other keyword in JavaScript for something. So it's getting, even though I'm using it, naming it, it's getting some. So if I were to just change this to like show, and then change this to show, it wouldn't have that highlight anymore. And the program, so I probably shouldn't use the word display since it's kind of conflicting as a keyword with something else. Do vectors use floating point numbers by default? Yes, they do, except for, so certainly in processing, the p vector class is defined with floating point fields, x, y, and z. JavaScript, there's really not a distinction between an integer and a float. There's just a number, and numbers could be an integer or a float depending on like all the flexible wonderfulness of JavaScript, or not wonderfulness depending on how you feel on a given day. But yes, everything's using floating point math essentially. Okay. How does programming in a group work is asked by Kunjung Sherpa. Okay, so programming in a group, a great way of doing that is using Git and GitHub as a tool. I mean, programming in a group, I should say, like, how does programming in a group works? It works probably best if you can all just hang out, have some lunch, some fruit, some tea, hang out in a room together, talk to each other, share code, draw on a whiteboard, be with people. Now, obviously a lot of large complex software projects worked on by large teams globally need some set of software tools to help facilitate that collaboration. And for me, currently that software tool is known as Git, and a web service, server service that you can use to work with Git collaboratively through the internet is GitHub. And I have a whole set of, probably if you just search GitHub Schiffman on YouTube, you'll find my set of tutorials about that. Okay. Andrew Kim asks, and Andrew Kim is going to be our set user as moderator. Andrew, I just set you as a moderator, so Andrew Kim has volunteered to try to be a moderator in the chat in case we have somebody who's very disruptive, which we had the other day. Andrew Kim asks, how do you use the vector's magnitude versus the angle? Great question. Okay, I love this. There's questions today. This is, by the way, what I had always imagined. Make videos, and those things where people could watch. Do live sessions where people could ask questions. I don't know. I like this. This is making me happy. Okay, so let's talk about magnitude. Oh, the one thing that's not making me happy is that this eraser. I'm doing my small part to kill the Earth because it seems that these paper towels work well to erase on this whiteboard, and that eraser does not. So I'm going to try to use this single paper towel today and not make too much of, not ruin the Earth. Hopefully I'm putting some good stuff into the world to counteract the bad stuff, like using too many paper towels. Okay, what were we talking about? Vector. Okay, so this is how one thinks of a vector in a two-dimensional space as an arrow, defining how to get from this point to this point. Code-wise, you probably noticed that vector is made up of an x and y component, v.x, v.y. There's also a z, and you'll see that actually when I do my Lorenz Attractor example. I'm going to use the z component. So this is really kind of what's there in the computer when you're programming with vectors. But a vector typically, in addition to being thought of as having components, can be thought of as a magnitude, meaning the length. How long is that vector? If you think of a force, is the force very strong or is it very weak? Is it a big, long vector or a short vector? And then also a direction, like am I pushing in this direction or in this direction? What's the direction? And that's often thought of as an angle. So when you make, in P5, you make a vector with create vector, you're making it typically with the components, with the x and y components. However, you can access both the angle and the magnitude through functions. So if this was a variable v, I can say v.mag, and this will return the length of the vector. And I can also say v.heading, and this will return the angle associated with that vector. I believe it returns it in radians or degrees, depending on what the angle mode is. Now, magnitude will work whether you're working with a two-dimensional or a three-dimensional vector. It's just the length of the vector. This heading function is only for two-dimensional vectors. I mean, it'll give you an angle, but an angle based only on the xy plane. So the direction of a vector in three-dimensional space cannot be defined as a single value because you need like Euler angles or quaternions or something that's going to make me turn off all the cameras and run screaming out into the streets of New York City, screaming, "Quaternions, help! They're after me! They're attacking me!" Okay, so that's heading is deprecated. Yeah, I don't think heading. So heading, it used to be called heading in processing. It used to be called heading 2D to emphasize that it was only for a two-dimensional vector, but now that's deprecated. Now it's just called heading. I've been talking for a half an hour. because that's when these cameras turn off. By the way, I'm using Canon 5D cameras, and they're being passed through this sort of black magic box as capture devices and then streamed out to YouTube. So this is the Mark II. I'm pretty sure if I ever could get my hands on the Mark III camera, it has a lot more features for doing this kind of like live streaming stuff. So someday, once I start my Patreon and raise a lot of money, I will get some better equipment. Actually, a lot of this equipment is on loan from NYU, so thank you to NYU for helping me with that. Okay. Okay, so Christopher Akiki asks, how is it you add velocities and accelerations and positions together? I'm sure I'm missing something in terms of dimensional analysis. Okay, so one thing is I should say that I'm pretty sure that is, this particular question is covered quite a bit in the Cadenze videos itself, so I'd encourage you to go check those out. But basically, adding vectors means, like I said before, putting them visually, it's putting them end to end. You know, obviously when you're adding numbers, you use the plus sign to say 5 plus 6 equals 11. If you have vector variables, the plus operator does not work with vector variables because the plus operator, the computer only knows how to interpret that as adding numbers. So there is, if you have a vector v1 and you want to add it, there is an add function. And so, so that's the way you add. Now, acceleration is the rate. Oh, this is perfect because this totally relates to this idea of differential equations that I want to talk about. But acceleration is the rate of change of velocity. Velocity is the rate of change of position. So acceleration gets added to velocity as velocity is changing over time based on an object's acceleration, and the position is changing over time based on the object's velocity. So this is like a perfect segue into the Lorenz Attractor stuff. But I'm just going to check the chat really quick before I get to that. Heading is a weird way to name that. I agree. It could just be direction. The reason why it's called heading is because typically you might use it to, let's say you have, I can just pull up, hopefully this is going to work. So this particular example, if you look at this is my flocking example, and I will, this will be covered in detail. Hey, where did everything go? Look at this, I got a bug report. Somebody file a bug on github.com/processing docs. The processing docs repository, tag @Schiffman in it, and say, I need to fix this example to have a wraparound so the flock doesn't leave. I don't know, I thought that was in there, but the borders function, for whatever reason, is not being called. This borders function to check if they're at the edges. So someone file that on GitHub, because I will fix that. But what I wanted to show you before they all run away is you can see each one of these triangles is pointing in the direction of its velocity. So as it moves, it's rotating in that direction. Oh, they're still here. They're going to go away. Are they going to come back now? I don't know. Maybe they're just, oh, wait, now it's working. Don't file that bug. Oh, maybe it's just working left and right, but not up and down? That's interesting. Look, go down, and they're not coming out the top. Oh, and it didn't even work. That's weird. Oh, maybe it works only on one edge. I don't know. I have to investigate that and fix that. But the point of what I'm saying is that you often want an object pointing in the direction that it's moving. That's its heading, so to speak. So you rotate by the angle of the velocity vector. Okay, Lucas King asks, this is maybe a dumb question. I 100% do not believe this will be a dumb question. But I was wondering what's inside the random function. How exactly does a computer generate random numbers? Oh my God, this is the farthest thing from a dumb question whatsoever. In fact, this is a phenomenally important question. And it is really a fundamental question to how generative algorithmic systems work and are developed. So, I would love to make a particular video maybe just on this topic and maybe implement some random number generation in a video. But let's just sort of say the key term here is pseudo-random numbers. So randomness, right? If you think about what randomness really is let me pull up my examples actually. So I'm gonna go in processing. I'm pretty sure that I have all my nature of code examples here. So I should have random graph. So, whoops, processing quit unexpectedly. Oh boy, okay, come back processing. Let me close this window. Okay, so what I want to talk about is random number generation. And I'm going into, so by the way, if you don't have the nature of code examples in your processing, you can get it by going to clicking add examples, and you'll see here, all you have to do is click nature of code and click install down here. But I've already done that. So what I'm looking for is in the introduction, I'm looking for a particular example called random distribution. Interesting. I think that's what I'm looking for. Random graph I was also looking, but let's look at random distribution. So I'm going to run this example. So what this example is demonstrating, let me run it, is it is picking a random number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, however many bars there are, and each time it picks that random number, it raises that bar. So if a perfect random number generator would give you a completely unpredictable random number every single time you ask for it, but over time you would get a perfectly even distribution of all numbers, right? It should pick the number 5 just as many times as it picks the number 8. So now, randomness, if you had some kind of like fancy machine that like measured the movement of electrons around like a nucleus, there's probably some like thermodynamic perfect randomness there that you could measure. And in fact, I think this becomes a question for like online gambling software, like a poker gambling software that needs to produce a random shuffle. If you could reverse engineer their random number generator, you could hack their system and know what cards are coming and do a lot of nefarious things. So I feel like I remember reading like an article about some like online poker company that actually had like a bank of like these machines that were bubbling up like gaseous particles and using that to measure randomness. But in processing, that's not happening. What's happening is it's using something called pseudo-random number generation. Oh, I wish I had a great prop here, which I'm going to refer to this in a second. So pseudo-random number generation is this idea of, oh, could we find a mathematical function that if you passed a number into it, it would give you sort of another number back, and if you fed that number back into it, it would give you another number back, and those numbers over time would exhibit the properties close to sort of perfect randomness. And that's what's happening. There's just a mathematical function. People probably spend their lives researching or their PhD dissertations inventing better pseudo-random number generation functions. But you can see that for as a creative coder, somebody making an art installation or whatever, it's fine if it's like, not the best, the most perfect random number generator. And over time, the random number generator that processing is using would in fact exhibit a pattern. Now, I'm going to show you, I think I actually, dare I say, I think I worked on some of implementing the random number generator for P5. So I'm going to go to, so I know where it is. I apologize if I'm wrong and somebody else did it. But I'm going to go into P5 under source, under math, and go to random. And you can see here, yes, there it is. So this is the random number generator function that's in P5. It is called a linear congruential generator, a variant of a Lehman generator. And you can look up this Wikipedia page called numerical recipes. And you can see that it is just some function. It uses some arbitrary constants, and then it runs this code and gives back a random number generator. And what's key about this, though, is that there is a seed. And what's so funny about this is, so random number generators need a seed, and the seed is the first number that's passed into it to get the first random number generator. This is actually incredibly useful because if you always want to get the same, you want to get random numbers, but you want to get the same exact sequence over time, you can set the seed. And there is a function both in processing and in P5 called set seed. So let's say you are making a generative poster design program, and your program generates these poster designs. And what you want is to run it a bunch of times and generate a PDF, and it's going to be random, but you want the exact same one every time, and then maybe you want a different one, or you want to be able to like go back and get the one you had before. You could always set the seed in your setup function. Now you could just set it to like the number 5 or the number 63. What's funny about this is P5, and P5 grabs a seed from like the native JavaScript random number generator if you don't give it one, which is kind of funny. It's using somebody else's random number generator to get your random seed for your random number generator. And if we looked up in the processing source code, I'd love somebody to go do that and let me know. You can see how it's seeded. There, sometimes random number generators are seeded based on like the number of milliseconds since the computer booted up, or the time of day, or the mouse location on the screen. You've got to come up with something that's kind of random-ish to use as a seed. Okay, so hopefully that helped. Is it a question? Here's another question. Actually, I probably missed some questions. Okay. Is it really important that you write unit tests for the programs you write? You are so asking the wrong person this question, because my answer is definitively no, it's not important. However, I'm sure there are many instances where it is quite important, and you'll see that large software projects that really need to be working and not have issues and are managed by large teams, having unit tests can be an incredibly valuable tool to, as you make a, what does a unit test do, by the way? So a unit test is something that runs separately when you make, so let's say you're building a library like P5.js and you change the code in the library. The unit tests are programs that run using your new version of the library and check to make sure things aren't broken. And they can do that by testing certain functions, knowing what the answer should be, seeing what the result is, and comparing it to the known answer. So what I would be wary of as a kind of prototyper, maker of things, sketching out ideas, you don't want to get so lost in making unit tests for your thing that you never make the thing itself. So, and a lot of things you're doing if you're making an interactive project, what I would say is more crucial than unit testing is user testing. So, you can get, is the program working? Does it make sense? Does your idea communicate what you want to communicate through user? So I would say user testing is really important. Unit testing, it sort of depends on the scenario. Oh yes, okay, so Andrew Kim mentions what I wanted to mention. I have this book, but it's at my office at ITP, so I don't have it with you. But I'll bring it up now, which is A Million Random Digits. So back in the olden times, let me just see if I can Google image search this. If you didn't have a pseudo random number generator or a supercomputer to generate your random numbers for you, and you wanted to do some type of what's often referred to as a Monte Carlo simulation, simulate out some idea with random numbers over and over again. This is actually a book published by the RAND Corporation with just like pages and pages of sequences of random numbers. And incidentally, you know how I was saying before in processing that these, what you want is an even distribution of random numbers? That's what you want for a pseudo random number generation with a, I don't want to say normal, because normal is another word for the Gaussian distribution. Uniform, that's what it is. This is known as a uniform distribution, where you have an equal probability of any number being picked at any time. But this is not always what you want. Perhaps you want to pick random numbers, but you want to pick higher random numbers more often than lower random numbers. When I get to genetic algorithms in my cadenze course, you want to pick randomly. You want to pick randomly from a population to make the next generation, but certain members of that population should have a higher probability of being picked. And then, of course, there are well-known distributions, and I'm going to try to. I think this particular sketch. This is the bell curve, or a Gaussian distribution. So if you want to simulate heights, let's say you want to simulate a collection of people, and you want to pick heights for those people randomly. Well, and you decide that in your alien world, aliens, forget about people, aliens are between 3 feet and 7 feet. Well, maybe there's a sort of average height around 5 feet. Yes, 5 feet, that's the average of 3 and 7. But most people cluster around the average. So you would want to more often have people that are around 5 feet and less often. So this is showing you the probability map of how often you want things. And that's known as, bell curve with, you can see, is there a Y distribution, a very thin distribution. I need to take a drink of tea here. I lost steam for a second. But hopefully that makes sense and helps you guys. Peter Kwan says that his company logo is a Gaussian curve. It's only important. This is Nuna Costa makes an excellent point saying it's only important to have unit tests if you don't want your flock of triangles to fly away. So yes, you can see that if there was some type of unit test to test the examples that are on the processing website, it might have caught that. But I would say another unit test for that is the collective consciousness, the collaborative, crowdsourced error reporting. Okay. So a 9cat fan asks how Andrew got moderator. So what happened the other day, just to mention, and I should check Twitch, I apologize. Galva Bart on Twitch asks if this is live. Yes, it's live. So that proves that it's live by me checking Twitch real quick. So something happened the other day where somebody came into the chat and was using some kind of offensive language and just filling up the chat with like a zillion comments. And I didn't notice it for quite a while, and then I went and just turned that person off. And so I think it's useful just to have somebody in the chat who can kind of make, as best as they can, just kind of decisions about that if we have someone that's there that's so disruptive that that they need to be muted. And so Andrew volunteered to do that, and I assigned him the moderator. If anybody else wants to be a moderator, you all seem like nice, lovely, trusted people. I'm happy to make all of you moderators. Okay, I don't know what you get to do as a moderator. It would be great if what you could do is alert me when my sound battery dies. But I have a new system of charging the batteries overnight, and I've got 3 bars each. Okay, so I've been streaming now for about 35 minutes, and I think I want to start getting to my Lorenz Attractor coding challenge. So I'm going to kind of poke around some URLs here and get set up for that. Okay, let's see, Lorenz System. Okay, so, first of all, if you guys don't know about Paul Bork, basically, Paul Bork has a website, I think, which outlines every single coding challenge I want to get to and just has an explanation of the code for it. So you really just turn off my stream, and I should just basically say, thank you, Paul Bork. If I ever make any money from this, I need to send you some royalties. Paul Bork, I'm just going to search Lorenz. So Paul Bork, and maybe I'll go to Paul Bork's main URL, has Paul Bork, I believe, is a researcher located in Australia, in Sydney, and has a lot of papers and pages, and a lot of these are from many, many years ago with very simple C code implementing a lot of these kind of classic computational algorithms. And so one that I want to look at today is the Lorenz Attractor, and you can see this is Paul Bork's page where there's a nice explanation showing the formulas. I want to talk about these formulas look scary, what do they mean? This is some of the example output. And then what I want to show you as I scroll down here is to show you he usually also always has just the kind of some really basic C code. And you can see that the C code is actually not drawing anything. It's just an algorithm that's printing out the XYZ coordinates of the result of that algorithm. So one thing I could do is take this and paste it into processing and translate it into Java and add the sort of drawing stuff. But I think what I'm going to do is when I do the tutorial is build it from scratch by looking at the formulas and trying to understand them. Because I think that might, in the end, actually be a bit more useful. But I want to make sure I reference Paul Bork's site because I have learned so much from this site. The other thing that I think is worth mentioning is so on the one hand, why am I here doing this? I think it's valuable to learn these skills, to unlock new ideas and possibilities in your head, be creative with them, play, experiment, and teach others. There's all sorts of possible things. I do know that there is this sort of thread, this conversation that happens in the kind of computational art world, so to speak, which is, is this like a cliche? Like if you take this exact algorithm, generate it, pick some colors, and print out a PDF of it and put it in an art gallery in the wall, is that good or bad or good? What have you done there? So I am going to completely stay away from that question. I do think that it's important for you to think about what's the context of how you're using these algorithms and why you're using those algorithms. But I'm going to leave that for you to discuss, to tweet at me, to discuss in another context that's different from this. And my goal today is really just the tutorial aspect of it. And I think there is a lot of value in recreating things that other people have made to discover something new, to learn about it, to be inspired by it, and also just as practice, so to speak. So that's Spectron asks, will videos be recorded? Oh, Spectron says, I feel like I'm getting ignored. Oh, I don't want that to happen. Okay, sorry, I see now there's a question. Spectron asks, I'll get back to the Lorenz Attractor. I don't want anyone to feel ignored. Can you link a random number on a range with random and transforming it into a normal Gaussian distributed random number? Okay, so this is a great question. How do you get that different range? This really merits a whole separate tutorial just about that. I definitely have some in my YouTube Nature of Code playlist, different distributions of random numbers. I recall making some videos like that. But for processing, the random function does not do that for you. It just gives you a uniform distribution. There is a function in processing called random Gaussian, which will give you Gaussian random numbers. There are Java classes for this. I'm sure there are JavaScript libraries and frameworks which will do this for you also. But ultimately, you need your own algorithm to specify, to manipulate the random number generator. And in the Cadenza course, I actually go over this also when I get to the genetic algorithms part. Okay. Yes. Okay. And Spectron, by the way, makes wonderful coding challenge tutorial videos in French. So if you're French, check out Spectron's channel. Okay. Now back to the Lorenz system. Okay, so that's my introduction to what it is I'm doing. Now, company I want to read a couple things to you guys, which I will keep in my head as I start. So the Lorenz Attractor was first studied by someone named Ed Lorenz. This is from 1963. Thank you, Paul Bork, for providing me with my materials to read. And it was derived from a simplified model of convection in the Earth's atmosphere. So what's interesting about these kinds of algorithms, something known as a strange attractor or a chaotic system, they're nonlinear systems, is that they are models of things that exist in nature where if you plug this sort of initial variables into the system, the output is deterministic, meaning it will happen exactly as the math dictates. However, if you change the inputs ever so slightly, the output will be wildly different. So that's sort of the chaos of it. It's unpredictable. It's nonlinear, meaning a slight change in an input value makes a massive change in an output value. This is also known as the butterfly effect, right? A butterfly flapping its wings, a slight change in the Earth's atmosphere would cause some major event, a volcano eruption on the other side of the world. Whether that actually happens with a butterfly is, I think, an interesting question to discuss. But that's the idea here. So this is an example of a system like that. Okay, now, those systems exist in nature. Those systems are defined by, and I'm probably going to repeat a lot of this when I start to record the actual video tutorial. Maybe I'm doing it already, but I want to make a kind of condensed version of it that focuses on the code. So I'm kind of talking it through to kind of remind myself how this stuff works, and I rely on you in the chat to say, actually, you're getting this wrong if you think right. So now, this all runs on a differential equation. So this is what I wanted to try to sort of wrap my head around trying to explain in the sort of creative coding context. Because you could definitely go and watch a kind of what is a differential equation video on Khan Academy or other math type lecture type materials, but it will be very focused on the sort of calculus path, derivative, an integral, first derivative, second derivative, that sort of more abstractly. And so what I want to try to describe, and I'm going to do this probably a couple times, is what is a differential equation, and what is a differential equation just sort of higher level, and how does this abstractly sorry, apparently I can't do the thing where I tap my head and rub my stomach because I can't think while I'm erasing. Why is a differential equation relevant to a creative coding context? So another resource that I think is useful for this is this particular URL, myphysicslab.com. I'm sure you could Google for this, and I'll include a link. What is a differential equation? And this, I think, is a really nice, succinct summary that sort of stays away from some of the kind of calculus aspects that are unnecessary for what we're doing, although important and interesting in their own right. I'm just checking. Nobody is complaining in the chat yet. A differential equation states how a rate of change, a differential in one variable, is related to other variables. So let's think about this in the context of nature of code physics simulation. You have a position, and let's just think of a position only as an x value. So position along a one-dimensional axis. You could say the change in x. So so this position can have a velocity, which is the change in x over time. This is often written as dx over dt equals something. This is essentially a differential equation. How do certain variables affect the rate of change of other variables? And let's see another. Let's look at this. This is described here as like a spring. A spring is a great. I'm sorry, I came over here. So a spring is a great. Is there anything like am I doing anything wrong by using other people's online materials to do this teaching? I don't know. Anyway, hopefully not. I would do this in the classroom, but somehow when I'm broadcasting this and then, I don't know. But hopefully I would be happy for somebody else to buy stuff that I put online. So I hope it's okay. I think, anyway, keep going here. The rate of change, okay, the rate of change in velocity is proportional to the position. So let's think about that in the spring context. So if you have a spring, which I could draw like this. I was actually thinking of a pendulum when thinking about this, but I think spring is good. So in other words, if you pull this out really far, if you stretch that spring really far, then it's going to spring back really fast. So its position, the velocity of this spring is relative to its position. So that's the differential equation. How is its velocity, the rate of change of its position, related to the variable position itself? So that's kind of like the basic idea of a differential equation. How does the difference of a variable affect? Let me look back at how that was described here again, because I said it wrong. The rate of change. The rate of change is the differential. And by the way, this derivative is another way of saying kind of rate of change. So in one variable is related to other variables. So that's the idea. So now, if I go to Wikipedia, we can see, this gives us a little more sense of what it means for what these Lorenz equations are. Lorenz equation is keeping track of the rate of change of a particle in space, in three-dimensional space. How does the x change? How does the y change? How does the z change? And it changes based on its position also. Its x, its y, its z, and some other constants. You guys are going to have to help me with this. Sigma, rho, beta. Did I get that right? That's the Greek letter sigma, lowercase, the Greek letter rho, and the Greek letter beta. Other half of my family is Greek. So I should know this stuff. Let's see. So somebody in the chat tell me if say you got your Greek letters right or you got your Greek letters wrong, because I would really like to know that. Okay, so I think so what I need to do now is translate this into code. So that's my introduction to the idea of what is the Lorenz attractor and what is a differential equation. And how does that relate to code? The next thing is to actually program it. So I'm going to, as much as I should probably practice programming it and then record and then start the actual lesson, I think I'm getting ready to do the challenge. I'm going to set the timer. I'm going to give a quick introduction and then refer to this and then start programming. So leave me your feedback or comments in the chat right now if I got anything wrong or anything was confusing or that sort of thing. I got my Greek letters right, somebody said. That's lucky. Okay, so I'm just going to erase the whiteboard here. I think I'm going to do the same explanation about differential equations. And then I'm going to refer to the Wikipedia page. And then I'm going to build the code. And let me actually run, I have a version of this example, which I cooked up this morning really quick. So let me open that. Is that open already or no? Sorry, open recent, it should be here. Strange Attractor, okay. So this is, I just want to have this running. Okay, so, oh, camera that went off, okay. So this is the, oh, I guess I made some changes to it and didn't save those changes. Because, whoops, okay, hold on, I have to fix a couple things. I want to have a visual reference running when I start. I swear I made these changes. Ah, weird. Did I restart the computer or change the name of it or save it somewhere else? That's really weird. Hold on, everybody. I have to, I'm just going to save this as underscore. And then I want to take this out. And I want to put, oh, that's right. Okay. I just want to check, make sure this is working. You know, why I lost the Z. Oh, right, okay. No wonder. Bear with me for a second, everybody, while I get this working. Okay, so this is essentially the example I'm going to build from scratch. And actually, I'm also going to do another thing here, which is translate by negative like 80, I believe would be the middle, if I'm right about that. Oh, whoa, 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 whoa. No, 0, 0. I want to put it back a little bit. Yeah, okay, that's good. I wanted to sort of rotate around the center. And so let me see here. Then I want to open a blank sketch, which I will program. Oh, I'm in the, let me just do save as Lorenz. Okay. 800, 600, this should work pretty well. This will be where my code is. This is a visual reference to start with. I should have this, maybe I should have this spinning automatically. Put that back in. Since, shoot. Here we go. Actually, I kind of want, should be this, right? Okay, sorry everybody, I just had to, oh no, I do want to rotate before I translate, yep. Okay. There we go. Okay, so this will be, oh, and you know what? I kind of want to be able to click the mouse and have it restart so I can, when I'm making the video. So if I click the mouse, it will set these things back and clear the array list. Oops. I'm about to be ready to do what I'm doing. Okay, so now if I click the mouse, it starts over. Oh, look at that. Is it starting in the right same place each time? Yeah, okay. Okay, just checking. I'm not sure X, Y, Z refer to position. Well, the thing is, okay, so I'm just checking. Okay, so Christopher Akiki makes a good point that X, Y, and Z don't necessarily refer to position, but I'm choosing to visualize the system according to position. And actually, if you go to Paul Bork's site, he has some sound files where the values that the Lorenz Attractor produces are used to like set MIDI note values, and it plays a little song based on Lorenz Attractor values. So you're right that they don't necessarily have to refer to as position, but that's what I'm choosing to use it, and that's how you'll get this visual result. Okay, so here we are about an hour in. The wiki says they are the state of the system. Yeah, so that's right, state variables. That makes it, I mean, they're defining the state of the system. So, and I'm visualizing the state. That's a good, I think that's an important point that I'm probably being kind of muddy about. I don't think I ate a big enough breakfast. I hope I'm going to be able to do this coding challenge. All right, the whiteboard is clean. I have my Wikipedia page. I have camera working. So all I really need is this. I could refer to these sites as well if I want to. And there we go. Okay, so I think, now I want to get the timer going. Again, I'm not going to do a timer counting down like I have some deadline I have to hit, but it's useful for me to just sort of see how long it takes and have a sense of it. And the ideas for these coding challenges, except for the multi-part ones, to be between 10 and 20 minutes. Because that's, I think, kind of a good attention span sort of thing. Okay, so I just need to add that in. Putting this here. There we go. So you should see it now. There, and then I just need to change this to stopwatch. There. So it should be in both shots now, the timer stopwatch thing. And this is here. And I can restart this. I need a... Okay. Yes, Matthew Van Den Heuvel asked, will you teach us to code it from scratch? This is exactly what I'm planning to do. I'm going to program it from scratch. Actually, though, I want to have that reminded me that I want to at least put in setup and draw and size, you know, I don't know, some arbitrary size. And I'm going to say, that's fine. I'll put in comments later. And there's something else about this that I wanted to do, which is the font size. Is this font size reasonable? Can you guys let me know? What do I have it at? 36. You know, often what I do is sort of zoom into the code anyway while I'm showing you a particular part. So let me know if that font size seems reasonable. Okay. 42 people are watching. I'm going to check the Twitch chat, which I've been ignoring. Yes. Everybody on Twitch, the most frequently asked question on Twitch, am I live? I am live. It is 12 p.m. right now in New York City. And Zorize asks, is the guy with glasses, that's me, the guy with glasses, live? Okay, here we go. Okay, thanks for your feedback. Okay, so I'm going to start this now. Hopefully not screw it up too much. Again, this thing will be, this I'm hoping will be about 10 to 20 minutes. And then I'll see what I have sort of time and energy for after in terms of questions. Yeah, so that's that. Have a little sip of this here. I have trouble getting started, as you guys can see and know. It's like, okay, here we go. So first thing I have to do is click, move this over. I have to click start here. Oh, and then I want, then I want this open. Oh, and I want the Wikipedia page. Okay. Yeah. I mean, the interesting thing about a differential equation is you're not solving for numbers. You're solving for a function that satisfies the differential equation. But I can't go too far down that road in this particular video because I want to focus on the code. But I would like to see if I could connect the dots a bit more with some of the math. Maybe somebody will have some suggestions for me. Okay, so here I go. I'll click start here. Hello, welcome to another coding challenge. In this particular coding challenge, I didn't get the thing didn't start. Let's start over again. Hello and welcome to another coding challenge. In this coding challenge, I am going to program the system you see over here on your right, which is the Lorenz Attractor system. What is it? Why does it exist? How does the math behind it work? And how do you write the code for the system from scratch? This is what I hope to tackle in about 10 to 20 minutes, and we'll find out at the end of this video how long this took. So there's a lot of references online that you could read about, strange attractors, chaotic systems, all that sort of stuff. I'm going to just sort of pull from the Wikipedia page and highlight a few key points and the formula before we start writing the code for it. So one thing that I'll point out here is that the Lorenz system is a system of ordinary differential equations. So first thing we have to answer is, what is a differential equation? So if you are a programmer here watching this video, you've probably maybe worked in processing or P5.js or done some other things. Let's think about an object that moves on the screen. You have a circle and it's moving. It has an x position that's changing over time. You might think of that x position as a variable called dx, and its actual x position is x. And you would say x equals x plus dx. So now, another way of thinking about how this system works is this idea. I got to start over. Sorry, everybody. I don't want to spend too much time on the differential equation part. And I was heading down a road that I didn't like. Let's try this one more time. You guys are very kind and patient to bear with me, but I kind of want this video to be particularly good. I don't know. I'm going to come back over here. Get myself set up again. Okay, oops, I got to close this. I also don't recall if I actually cycled the cameras. Whoops. And hold on a second. Make sure this is working. Oh boy. Ah, shoot. I gotta fix. Now I screwed this up. I'm putting the timer in the right place again. And put that down here. Okay. Okay, sorry about that, everybody. Is this working? Yes, and okay. Rate of change of one. Sorry. How the rate of change of one variable is affected by other variables, and then what is the rate of change? Spring example, that sort of thing. Okay. I see things are happening in the chat. I don't know what they don't seem to be related to what I'm doing. Okay, here we go, everybody. Sorry about that. I'm going to try this again. Hello and welcome to another coding challenge. In this coding challenge, I am going to implement the system you see over here on the right called the Lorenz Attractor. Visualize that in 3D, in processing, all in one session here, which will hopefully be about 10 to 20 minutes. We'll see how long it takes. I've got a timer running up there. Okay, so before I start actually writing the code for it, I want to talk about what this system is, why does it exist, why is it interesting, and how does the math behind it work on a kind of higher level, and then we'll start looking at the formulas for it and implementing those formulas in code. Okay, so the Lorenz system, there's a lot of resources for this online. I'm going to put a few in the description of this video. Paul Bork's site is a particularly useful one that I'll just mention really briefly, but I'm going to look just at the Wikipedia page here, which says the Lorenz system is a system of ordinary differential equations. Okay, so the first thing we have to tackle here is, what is a differential equation? I could easily, I got a timer running here, I could easily be here for like the rest of the day talking about differential equations and confusing myself over and over again. But the basic idea of a differential equation is an equation that looks at how a certain variable changes according to other variables, how the rate of change of a variable is affected by other variables in a system. That rate of change being a differential. So let me give you an actual practical real world example that might help solidify this understanding. Let's say you have a spring, okay? So I have a spring connected to a wall with a bob at the bottom. And you could think of this spring as having a position called y. How does its y position change over time? That's often written as the change in y over time. You could think of that in programming speak as y equals y plus the change in y, right? Every frame of animation, y changes. But it changes based on its the rate of change of y actually changes based on the y position itself. If you pull it all the way down here, how fast it's going to spring back is going to be much more than if you pull it over here. So dy over dt, the change in y, the differential of y, is a function of other variables in the system itself, y itself. This is a differential equation. And so this actually comes up all the time in programming. You have position, you have velocity, velocity being the derivative, the rate of change of position. This is something that you'll see over and over again. And here, the Lorenz system is defined by these particular differential equations. The rate of change of x over time, the rate of change of y over time, and the rate of change of z over time. Now these variables, x, y, and z, those define the state of the system. But I'm going to use those literally as x, y, z positions to visualize to get this particular structure. So if I look at those values, the state x, y, z over time, and draw them with colors and lines, I'm going to see this particular system. So why is this system interesting? It turns out that the Lorenz system, which was invented or discovered in 1963 by Edward Lorenz. He was studying meteorological conditions, the flow of the atmosphere, this type of thing. It's one of these chaotic nonlinear systems, meaning whatever the inputs you feed into the system, you feed some inputs into the system, you calculate that system over time. It's a deterministic system that will produce an exact result every time with the same inputs. But if you change the input ever so slightly, you could get a wildly different output. It's nonlinear. A tiny change to the input makes a large change to the output. This is the butterfly effect. A little butterfly flaps its wings, changing the air just a tiny bit in the outside on one side of the world, and on the other side of the world, a giant volcano erupts. Okay, so this is this idea of a nonlinear system. It's chaotic, it's unpredictable, and a lot of these types of systems exist in nature, and this is one particular example of a model of that type of system. Okay, so now let's look at these formula, and let's try to figure out how we're going to actually make this happen in code. I think we're ready. So we know that I need three variables, an x, a y, and a z. So let me go to my program here, and I'm going to close this one, and I'm going to start writing some code from scratch. And I am going to give myself an x, and a y, and a z. And I'm going to give them some initial values like that. Okay, so we're good. So I solved those equations. I know I need an x, a y, and a z. So that's a good start. Now, one thing I should mention really briefly as I'm about 5 minutes into this is that notice I defined those values as floats. If you look at examples you'll find on the internet, often the data type that will be used is a double. A double being just like a floating point number but having more decimal places. And sometimes with these systems you really need a high degree of accuracy. But I'm just some person here on the internet programming colors and things on the screen. I don't care if it's a little bit not so accurate. And float is a bit more native to processing, so I'm going to use floats. Okay, so now what I need to figure out is I want to kind of implement these equations. So let's just start with x. The change in x over time equals sigma, that's the Greek letter sigma, times y minus x. So first of all, I can't use the Greek letter sigma easily in my code. So sigma, I'm going to make A, rho, I'm going to make B, and beta, I'm going to make C, which I realize is a bit confusing, but that's what I'm going to do. So those are constants, by the way. I need constants for those values. So let me go back to my code, and I'm going to say a float A equals 1. So I'm just going to start with the constant 1. Now, what I'm going to do is have this particular calculation happen over and over time, right? It's supposed to happen over time. This is the interesting thing about this. Those formulas, the change in x over time, those formulas are talking about real life time that's continuous. Our time in processing is frame by frame by frame. So every cycle through draw is 1 unit of time. So what I'm going to say is that the change in x equals that constant times what? Y minus x. Y minus x. And now x equals x plus that change in x. It's really that simple, right? I'm just taking that exact formula that says the change in x over time equals the constant times y minus x. And now change in x just means change x by that value. X equals x plus dx. So I can actually start to go and implement y and z, the change in y and the change in z. And now I just need to go back and refer to those formulas again. X times b minus z minus y. Oh God, I hope I get this right. This is hard to do. Oh no, sorry. X times b minus z times y. Did I get this right? Minus y. I want to have spaces there. What's wrong here? Oh, it doesn't know what b is. I'll fix that later. And now the change in z is x times y minus c times z. So it's x times y minus c times z. So this should be good. And now I just need to get some spacing here. And I need to also add 2 more constants. Float b equals 1, float c equals 1. And now I need to just change x, y, and z. X, Y, Z. X, Y, Z. Y, Z, dy, dz. Okay? So this is the idea. I implement those formulas directly from the Wikipedia page to calculate the change in x, the change in y, the change in z, and then actually change them. Now here's the thing. What is my time? There's a weird sort of thing that I'm going to bring up here, which is my time step. So right now, every frame is like a singular unit of time. But the pattern that I'm going to draw, right, is going to look, I'm not going to be able to, it's going to look something like this. And in the sort of continuous world, I was moving this marker continuously. But in the processing animation world, I have point, 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 point. So how close, and I might connect those with a line. So do I want to see my result look like this? Or do I want to see it as a more continuous curve? How fine do I want those to be? And that's the sort of dt, right? If you think about, oops, I'm going to come back over here, right? Really, I'm saying dx over dt equals something. So what I want to do is actually take that something and multiply it by dt. What is the change of time for each frame? So what I'm going to do is also introduce a variable called dt. And I'm going to say it's like 0. I'm just going to make that 1 for right now. But I'm going to take the whole thing and multiply that by dt for each one of these to sort of scale. And I'll show you how different that's going to look as I continue doing this. So now we've got those formulas implemented. Now we've got to see, is anything working correctly here? So I need a way of figuring that out. The first way I'm going to do to figure that out is first just make sure the program runs. I'm going to add a black background, and I'm going to run it. And okay, so I don't have any errors. That's a good sign. One thing I could do is I could say print line x, y, z. So I could sort of look at what's being printed out. Now notice something here. All I'm doing is getting the values of 0. So there's a little bit of an issue here, which is that doesn't make any sense. So I can't start with 0, 0. If I start with 0, 0, 0, these formulas are only ever going to produce 0, 0, 0. So I got to modify the inputs a little bit. And I'll just start with x as like 0.01. That should do pretty well. And if I run this again, we should see, like, look, I'm getting some interesting values there. Now, what are these values producing anything of note? Not really, but why not? Well, because my constants, I just made my constants 1, 1, and 1. So the Lorenz attractor works a particular way based on what those input constants are. So if I go back to the Wikipedia page, I could sort of find somewhere on here, it's going to give me some values I could use. Like sigma equals 10, rho equals 28, and beta equals 8 divided by 3. So let's use those constants. I believe sigma was A, B was 28, and C was 8 divided by 3. And I'm going to do that just to make sure I get a floating point value. Okay, so I think that should work. I'm like skeptical. And we should see, ooh, not a number. Okay, so what have I done wrong here? I might have to time out this video. See how long this debugging takes. And this might get edited out if it starts to take a really long time. But let's look here. So what have I done wrong here? X, Y, Z. So let's comment out and just do X for a second. And see what I get. Oops, and I just want to look at X. Oh, I had some numbers, and then I got not a number for Y. So I might just be like, 1 is a terrible number for dt, because I'm like, it's as if I'm teleporting myself through time massively fast. So let me just make this 0.01. Yeah, okay, this is more like what I expected to see. Well, those numbers are getting incredibly small. I hope I implemented this right. I have to check my formulas. But let's go back here and see if I'm getting some reasonable formulas. Okay, good. Okay, so this is better. This is what I expected to see. Okay, great. So now I'm seeing some numbers that make more sense. So my issue there was literally just having, and maybe that won't get edited out, was just having the number 1, and it just sort of went off to infinity super fast. These systems, they don't have a recognizable repeating pattern, and they'll often tend towards infinity or some like non-existent value. Okay, so let me go back to 0.01. Now I want to be able to figure out, is something actually working here? So the first thing I'm going to do is just say stroke 255, and I'm also going to translate to the center of the window. And I'm just going to draw a point, and I'm just going to do this in 2D. So I'm not going to worry about the z. I just want to at least see, like, let me plot the state of the system over time with x, y. So let's do that. And, good, this is very good. So it looks like I did the formulas correctly, and you can start to see, like, that's something there. So we're kind of like, we're trucking along here. I've got the Lorenz system, like, sort of visualizing right now. So really, basically, I'm done. However, I want to make this look like something. I want to make this look like a 3D shape. I want to maybe add some color to it. I want to be able to spin around it. I need to do more with it. Maybe I want to be able to like explode it so that all the points should like fly off of it and come back. So I want to do, even though in 13 minutes we kind of got the math down, I want to do more with this in terms of the visual output of it. So let's go forward with that. So the first thing that I'll do is let's just go ahead and work in 3D. So I'm going to change the renderer to P3D, and then I'm going to add the Z point. So we should see now that it's the same. It looks pretty similar, but there's actually a Z value there. Now, one thing I want to add also is just, I want to use the processing function scale. So scale is a transformation you can add to your scene to kind of like stretch it out a little bit. We might be able to get this through zooming in and out as well, but I just want all the points to be sort of spaced out a bit more and look a little bigger. So I'm going to basically scale everything by 5. So we can see, yeah, so this looks, so now I kind of have a bit of a closer view. You can see all the points of the Lorenz Attractor are being plotted in 3D. Now here's the thing. How am I getting all these points on the screen? I'm just drawing one point at a time. Well, notice how my background is in setup. So this worked just to see that the system was working, but it's not going to be a very good solution for eventually over time being able to manipulate this system. So what I need is some sort of data structure, some sort of list that I can store all the points of the Lorenz Attractor. So let me do that. And what I'm going to do for that is an array list. And this is where we might rather be in JavaScript, and I'll try to make a JavaScript version of this as well. I'm going to call that points. I'm going to make that a new empty array list. So this is the syntax for something in Java called an array list, which is a flexibly sized array, something I could just add to. And I'm calling it points, and the data that I'm going to put into that array list are p vector objects. Why do I want a p vector object? It's because every single frame, I'm going to say points.add a new p vector with that x, y, and z. Okay? So I want to add a new vector with x, y, and z to that particular array list. And we can see that this is still working. Nothing is broken yet. And what do I want to do now? As those points are being added over time, I want to draw all of them because I need to erase the background, right? So let me just show you what I mean. I'm going to move this background to draw. This is actually going to produce kind of an interesting result because now you're going to see this point. I kind of love this. Just moving along the pattern of the Lorenz Attractor. It's kind of this beautiful, interesting, kind of chaotic motion. I just want to stop and watch it. But I'm 15 minutes in. I want to see if we can wrap this up in about 20 minutes. So I'm going to keep going. So what I want to do is instead of just drawing the existing point, what I want to do is say for every vector v in that array list points, draw a point at v.x, v.y, and v.z. So I'm now saying instead of just drawing the current point, loop through, and this is known as an enhanced loop in Java, for every vector v in the array list points, draw a point at vx, vy, 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 vy. Back after a technical hiccup, you can see that the entire Lorenz attractor is drawn with each element as a separate point based on every p vector that's in that array. So really, essentially, I'm done. There you go. It's in 3D. That's the entire Lorenz attractor shape. But I do want to add some more things to this and give you some exercises to think about what you might do with this. So first, let's just change the way we're drawing this a little bit. One thing that I could do is connect all of the points with a line. So instead of drawing everything as a single point, I could actually set the vertex of a shape. So if I say begin shape before I draw all the points, and end shape after I draw all the points with vertex instead of point, what that's going to do is connect every point. And you're going to see now that, whoa, it's doing it, but it's actually trying to fill it in as if it's an entire shape. So there might be some interesting things I could do with that, but for now I'm just going to add no fill. And we're going to be able to see now this continuous line. So I could zoom into it and sort of see that every point is now connected, right? So now we have this continuous shape, which is a nice start of sort of seeing how I could sort of tinker with how this is visually. I could also try to come up with like a clever way of changing the colors of it. I'm sure that you, as a wonderful person on the internet with visual design talent, will do something much more interesting. But I'll just show you really quickly. I already have that in there because that was from the technical glitch. But I could add something called color mode. And I could change the color mode to HSB, meaning hue, saturation, brightness. So what I could do is set the stroke with some sort of hue, a saturation of 255, the maximum, and a brightness of 255. So I'm now as I draw it, it's going to have a particular kind of like turquoisey, greeny hue. And why not, while I'm doing this, make a variable, start it as 0, have that variable be the hue, and for every single vertex, increase that by some value, and then if it goes above 255, reset it back to 0. And now I should get, why not have a rainbow, since this is coding rainbow, a rainbow Lorenz attractor pattern. So you can see as the color is changing, we've got kind of yellow, red to yellow to orange, and that sort of thing. So really, okay, so the last thing I want to mention. So what's interesting about what I'm doing with this particular strategy, separate from the Lorenz attractor, algorithm itself, is the fact that every one of these points is saved in memory in that array. So one thing I might just demonstrate to you is the fact that those points can be manipulable in real time. So for example, one thing I could do in processing is I could write a vector called offset. And I could say pvector.random 3D. That's going to give me just a random unit vector of unit 1, of length 1, pointed in a random direction. And I could add that offset to every single vector in the Lorenz attractor. Now if I run this, it's kind of going to go crazy because the unit of I've scaled up by 5. So you can see it's like shaking and jiggling like crazy. So what I could do is maybe shrink that offset down quite a bit by, make it 10% of the length of itself. And you can see now, if I zoom into it, you can see how the points are kind of moving ever so slightly in space. Now, I'm not suggesting that what I've done is a particularly magnificent result, but what if you had all those points move along a sine wave? Or what if you had those points expand out and then come back to their original location, or morph into another shape, or fill in the blank of your interesting idea there? So what I think I would like you to do, now that you've seen how to program this Lorenz attractor from scratch, first, you don't have to do anything. You're just watching this video. Maybe you want to go outside and toss a Frisbee around or eat some lunch, which is what I kind of want to do right now because I'm feeling a little woozy. But I think what would be interesting, what I'd be excited for some of you watching this video to explore is what types of how can you put your own design spin on this particular shape? What happens if you start to manipulate the variables, right? Here are the constants that I'm using. Make up your own constants. Look up on the internet some other known constants for the Lorenz attractor that produce other kinds of shapes. What happens if you change the dt variable? Can you mess around with these formulas and get something else? Could you go to a site and find a different kind of attractor that's not the Lorenz one? There's a lot of these under the sort of category of strange attractors. So try to make your own version of this. be creative, play, experiment, don't worry too much, and share with me your results. But this has been, hopefully, something you've enjoyed, which is programming the Lorenz Attractor from scratch in processing in 3D. Thank you very much for watching. I'm thrilled to have finished this because you might not know there was about a 45-minute audio problem. I really hope the audio is working right now, and this is actually the end of this video. Thanks for watching, and I'll see you in the future in another video. Goodbye. Okay. Ooh, that's a great suggestion in the chat by Mesam Musavi. Says animate a camera along the path. That would be really cool. Okay, I think I did it. I don't know to what extent those, I kind of had lost my momentum and rhythm so much, but hopefully when it gets put together, it'll be a reasonable video tutorial. And I could always someday do this one again, as I say for everything. So I've gone for about 45 minutes longer than I had meant to today, just because I really wanted to make sure this finished. And unfortunately, this was the only video tutorial I made, although there was a lot of interesting stuff at the beginning, hopefully about like questions from the Cadenze course. So a couple things I want to mention. Next week, I am traveling to the great country of China. I will be in the city of Shanghai. I've never been there before. I'll be there for a week visiting NYU Shanghai. There's an interactive media arts program that has their big end of semester show. I'm going to see their show. It's unlikely I'll be able to live stream from there. I do hope to record 1 or 2 video tutorials. They'll probably just be screen captures, which maybe are just as good as my ridiculous system here. So I'll have some new content. I'll be on Twitter and on email and that sort of thing. Don't email me. That's my one request out of life. Twitter is great. The processing forum is great. The forum for the Cadenze course is great. I can't deal with email. But you should email me, and you should not listen to me. No one should listen to anything I say. I want to be in touch with you watching. Please, if you make something from this, let me know. Be in touch. I will publish at some point, hopefully in the next 24 hours, this video tutorial will go online. I'll probably leave the stream archives online somehow. There'll be 2 of them, I guess. This one that worked is the second half and the first half, and I'll try to link between them somehow, figure it out. But I'm rambling. I'm really exhausted from this, and so I think I'm going to go. I'm going to check the Twitch chat. I will need a VPN. Yes, I do have a VPN for while I'm there. If you have any suggestions for things that I should make sure to see in Shanghai, I would love to hear them. Food that I should eat, a particular restaurant or a place to go to, let me know. I'm only going to be there for 1 week. I'll be back May 15th. And when I get back, assuming I don't continue to have these technical problems, I'm going to start a Patreon, I think, to just, now that I've been doing this for long enough, I feel maybe ready to think about funding this a little bit, for myself, and also to be able to have some flexibility to spend some money on getting better equipment or better people helping like write descriptions, and that I already have too now. So anyway, if you have thoughts about that, let me know. The real thing that I can't figure out is whether to do, I'm leaning towards having the Patreon be a charge per live stream or per week that there is a live stream, or I could do a monthly thing, but I'm just a little bit afraid, like what if I go away for 2 weeks? I don't want people to be charged for the monthly thing. So I'm really thinking about that. If anybody has any clever ideas, let me know. Okay. Do something with the heat. Okay, so I thank you for being so patient. I apologize for your ears that got blown out. I hope you're enjoying this and finding this useful. Send me your feedback. Get in touch on Twitter and in the YouTube comments, or in the Cadenze forum, or in the processing forum. And I'll see you all sometime soon. After May 15th, I will not be live probably until May 15th, I think, is a Sunday. So sometime that week, possibly not till like the 18th or 19th, like Wednesday or Thursday that week. Thanks very much. And you can sign up. If you're still watching this and you want to know, if you want to get notifications, if you go to schiffman.net, you can sign up for email notifications when there's going to be a live stream in the top right corner. Okay? And I always post on Twitter @Schiffman. Goodbye.